Hello, students. Welcome to the seventh lecture on particle physics. And what we saw yesterday in the sixth lecture that observed particles are broadly classified into two groups, fermions and bosons. And we have further classification of fermions into baryons and leptons. And then for bosons, we have mesons, mediating quanta, and Higgs boson. And now, today, we are going to discuss the various conservation laws in particle physics. And there are two types of conservation laws in particle physics. One is known as exact conservation law, and another is known as approximate conservation. What are the exact conservation laws? These are fundamental principles and has to be followed by any interaction processes. The examples are energy, total angular momentum, linear momentum, and charge. And then we have also lepton number, baryon number, and charge conjugation, parity, time reversal, all taken together. Therefore, these are the 7 exact conservation laws in the standard model of particle physics, where these 4 are given by nature. We cannot violate them. But the other 3 are in the standard model, where one is obeying lepton number conservation, baryon number conservation, as well as it conserves charge conjugation, parity, and time reversal, all 3 taken together, and whose consequence is that the mass of the particle will be the same as mass of the antiparticle, lifetime of the particle will be the same as the lifetime of the antiparticle, and the magnitude of the magnetic moment of the particle will be the same as the magnitude of the magnetic moment of the antiparticle. Now let us start discussing the other conservation law, which is known by the name approximate conservation law. These have been introduced by us to understand or to classify the different interactions in nature, and whether all the conservation laws here we are going to talk about, like isospin conservation, third component of isospin, strangeness conservation, charge conjugation, parity, charge conjugation and parity, these two together, and time reversal. Again, there are 7 approximate conservation laws. Therefore, we have 7 exact conservation laws in the standard model and 7 approximate conservation laws. Now, isospin and third component of isospin, this isospin algebra was developed in an analogy with the spin algebra that we have, but this is not a vector in the ordinary space. This is vector in isotopic spin space, which is a hypothetical charge space that we shall discuss. Therefore, these 7 are the approximate conservation laws, and in a strong interaction, all these 7 are conserved. While in electromagnetic interaction process, isospin is not conserved, while the other 6 fellows, they are conserved. While in weak interaction, all of them get violated. Therefore, these have been introduced to classify or to understand the various processes that occur in nature. Now, among the exact conservation laws, the laws governing the preservation of energy, total angular momentum, linear momentum, and charge are inherent requirements of nature, universally binding and imperative for all phenomena to adhere to. You cannot escape it. While the laws of conservation of baryon and lepton numbers and the conservation of CPT are the requirements of the standard model of particle physics. The consequence of CPT that I have discussed is that masses, charges, lifetimes, magnitude of magnetic moment for particles and their antiparticles will exactly be the same. That means charge of the particle will be exactly of the exact magnitude as that of antiparticle. Observation of any violation of them will require a theory beyond the standard model. Similarly, any observation of neutrinoless, for example, double beta decay, like a radioactive nucleus ZXA is decaying into a daughter nucleus by emitting two positrons, or another nucleus that is decaying into two electrons without accompanying any neutrino, that will be an example of neutrinoless double beta decay. Because what we have been taught in nuclear physics, that beta decay is a process where a nucleus changes to another nucleus, say Y, by emitting a positron and a neutrino, or a nucleus, say ZAP, is decaying into another nucleus, Z plus 1 AQ, plus by emitting an electron and a neutrino, anti-neutrino. Therefore, this is beta plus decay, this is beta minus decay, or this is in literature is known as negatron decay, and this is known as positron decay. As we have a positron in the final state, we can have also a nucleus where a nucleus, say, decays into another nucleus by emitting two electron and two anti-neutron. This is where you have two electrons and two anti-neutrino. But what you see, that we are conserving charge, we are conserving the baryon number, because A represents the number of proton plus number of neutrons, and they are the same. Therefore, the number of baryons in the initial state is the same as the number of baryons in the final state. And then we have two electron-lepton number conservation. We have two electrons and two anti-neutrino. And here, like, we had one positron and one neutrino to conserve lepton number, one electron and one anti-neutrino. And here also the example which I gave, that they had the same A. Mass number was not changing, and that means proton and neutron numbers, they are not changing. But in the case of neutrinoless beta decay, you won't have this guy. You won't have any neutrino in the final state. And there are many experiments in the world which are going on, which says that neutrinoless beta decay should be an observed process. And if we happen to observe a neutrinoless double beta decay, then what we'll say that we need something beyond the standard model. It is not that physics is going to change, but the main point is we need something beyond the standard model. That is all. Then we have conservation of energy. This has been taught to us in 7th and 8th class, that the total energy, you cannot create or destroy it, only it changes from one form to another. In particle physics, the principle is evident in the transformation between different types of particles during their interactions. Energy can be converted among kinetic, potential, and rest mass energy, but the total energy remains conserved. For example, I have given it to you earlier that a neutron decays to proton, a free neutron decays to proton, electron, and anti-neutrino, but a free proton does not decay into neutron, positron, and neutrino, because mass of the proton is smaller than the mass of the neutron. Similarly, if we talk about a beta minus or beta plus decay, then while in a nucleus, when we have nucleons which are in motion, we have the conversion of proton to neutron or neutron to proton. Then we have conservation of momentum. This says that the total linear momentum of the system in the initial state must be equal to the total linear momentum of the system in the final state. That means if I say that Pi equal to 1 to n Pi, that must be equal to some j equal to 1 to k pj for the particle 1 plus 2 plus 3 plus n, and here that is 1 plus 2 plus different particles plus k. The total linear momentum of the initial state must be equal to the total linear momentum of the final state. That is the linear momentum conservation rule. And if we take them together, the energy conservation and linear momentum conservation, and take a simple example of pions decaying at rest. Suppose I have a pion, pi plus, that is decaying into mu plus plus nu mu. Now this is decaying at rest. Decaying at rest means its linear momentum p pi is 0. And that means from linear momentum conservation, since p pi is p mu plus p nu, therefore what does this implies? That p mu is equal to minus of p nu. That means this is a pion and this is decaying into a muon and a neutrino, and they are moving exactly in the opposite direction to conserve momentum. That means their magnitude of the momentum would be the same. Only they will be emitted exactly in the opposite direction such that p mu plus p nu should be equal to 0. This is important, and this minus sign is just representing the fact that these two particles are getting emitted in the opposite direction to conserve momentum, while the magnitude of the momentum will be the same for both the particles. Now if we are saying that magnitude of the momentum would be the same, and then we are applying energy conservation for this pion decay, therefore if you look at this guy and these two, energy conservation will tell us that total energy of the initial state must be equal to the total energy of the final state. E pi will be equal to E mu plus E nu. Now, E pi, pion is at rest, therefore its rest mass energy, its energy will be its rest mass energy, its kinetic energy will be 0, and therefore this will be equal to m pi c square. We work in the units of c and h cross, that means we put c and h cross equal to 1. Therefore, instead of m pi c square, simply we write m pi, or instead of e square as equal to p square c square plus m square c4, we simply write it as p square plus m square, and we say that these are in the natural units. Therefore, if we are working in the natural units, simply we write it as m pi, or E, instead of writing for example, if I am writing it for massless particle, simply we will write it as E is equal to P, though it should be E equal to PC. But in natural units, we put C is equal to 1, and or similarly we put H cross is equal to 1, and instead of writing it as E is equal to H cross omega, we write it as E equal to omega. Therefore, we have m pi, this is equal to energy of the muon plus energy of the neutrino. And what is energy of the muon? This is p mu square plus m mu square. And energy of the neutrino, in this term, since neutrinos are massless particle, therefore its energy is the same as the momentum, and this is equal to p nu. And for massless particle, p nu is the same as E nu. Therefore, m pi minus E nu, this is equal to p mu square plus m mu square. And mind it, the magnitude of muon momenta is the same as the magnitude of neutrino momenta. That means this I can replace with p nu, and p nu for the massless neutrino I can replace it by E nu. Therefore, for all practical purposes, I can replace this square root by E nu square plus m mu square. Therefore, we have m pi minus E nu as equal to square root E nu square plus m mu square. Now I do the square of on both the sides and expand it. What we will get is the following. This will give us m pi square plus E nu square plus twice m pi E nu from here, and on the right hand side we will have E nu square plus m mu square. Therefore, E nu square from both the sides will go away and we will have E nu as m pi square minus m mu square upon twice m pi. Therefore, for a two-body decay, A going to B plus C, it is decaying at rest, then we can have this thing, and here one of the particle is massless, and therefore what we are seeing that E nu is m pi square and minus m mu square by twice m pi. We have applied linear momentum conservation and then we have applied energy conservation, and we are seeing that neutrino energy is being expressed in terms of the rest masses of the particle, and that means the neutrino energy will be unique because the rest mass of the particles, they cannot change. M pi is 140 MeV, mu is 105.6 MeV. From here exactly you can obtain what will be the energy of the outgoing neutrino. Take m pi approximately as 140 MeV and m mu as 105.6 MeV. You can obtain the energy of this neutrino. Now this is the neutrino energy, and take it as a homework and obtain what will be the muon energy. That will also be in the rest in units of the rest masses of the particle, and just use the same energy momentum conservation rule. You will find that this will be also function of m pi and m mu. So therefore, this is how we use energy momentum conservation, and this is the example which I have taken. A particle X is decaying at rest and we have an electron and a Y in the final state. Therefore, the four momentum conservation, because what is four momenta? This consists of energy and the three momenta. Therefore, when we are saying that we are applying the condition Ex is equal to Ey plus E, energy conservation, and the three momentum conservation, Px is equal to Py plus Pe, we can combine them together to write the four momentum conservation, that four momenta of the initial state must be equal to the four momenta of the final state, Py plus Pe. Therefore, if I talk about particle X at rest, therefore this guy will be at rest and Py in magnitude will be equal to Pe, and that we may call it as P. Therefore, a nucleus X is decaying into Y and an electron without the third particle in the final state. And why I am giving you this example, we have already discussed it earlier. In pion decay, this is because of the following reason. As you can see that if we consider a particle X decaying into Y and electron, what we are saying that the electron's energy, like I had given you an example of muon energy, the electron's energy will be expressed in terms of the masses of the particle, where X is the mass of the parent nucleus, X, Y is the mass of the daughter nucleus, and ME is the mass of the outgoing electron. Therefore, what we are seeing that electron's energy is being expressed in terms of the rest masses of the particles, and that means this electron energy will be unique. No matter 2 electrons or 5 electrons or 10 electrons will be emitted in beta decay, all those electrons will have unique energy. I am plotting energy of the electron on the x-axis and number of emitted electrons on the y-axis. What we are seeing that suppose this value is say something x here. Then first electron, second electron, third electron, fourth electron, fifth, nth electron. All of them will have unique energy, and that means this guy will be parallel to the y-axis, and that means this spectrum will be a discrete spectrum. Therefore, if a particle is decaying at rest, a nucleus is decaying at rest into 2x is decaying at rest into y plus an electron. This could be, I can write here zxa, and this will be z plus 1 y plus electron. This you may take any example of radioactive nucleus here. What we are finding out that if this is a two-body decay, then the energy of the emitted electron should be unique and the spectrum should be a discrete spectrum. That means I am talking about this red line which is expected if only there are two particles in the final state. But what happened in 1912, 13, etc., that when people observed nuclear beta decay, instead of a discrete spectrum, they found the spectrum to be continuous. And that means there was a problem. And therefore, what was one thing? That a nucleus X was decaying into, say, Z plus 1, Y plus electron. Expected line was that all the energy of all the electrons will be unique and we should get a discrete spectrum, while when experimentally it was observed that this spectrum is not discrete, this spectrum is continuous in nature. Besides that, the other important point was that the angular momentum of the initial state was also not equal to the angular momentum of the final state. Mind it, we have said in the exact conservation law that angular momentum, energy, linear momentum, angular momentum and charge, they have been given by nature and we have to obey them. Therefore, what was found that the angular momentum of the initial state was not equal to the angular momentum of the final state. And for example, this spin was an integer, while if you talk about this guy, this was of half integer multiple, this was int, and this is, we know that all electrons have got a spin half. Therefore, what was found that this is integer, one is violating angular momentum conservation law. Therefore, Ji was not equal to Gf in the analysis. And therefore, there was crisis of energy angular momentum conservation rule. This experiment was repeated for the other nuclear beta decay processes, and everywhere it was found that no, the spectrum is continuous and we are violating angular momentum conservation law. I will talk about this spectrum again when I will introduce neutrinos. To save this angular momentum conservation law, in 1930, Wolfgang Pauli introduced that a new particle, which initially he called as neutron, which later was rechristened by Enrico Fermi as neutrino, when Chadwick observed today's neutron, a member of the nucleus. This neutrino was conjectured by Wolfgang Pauli in 1930 in order to save energy angular momentum conservation law. He argued that in beta decay there are 3 particles in the final state instead of 2, and that particle is almost massless, and that particle is a spin half particle. Therefore, a spin half particle which is almost massless was proposed by Pauli in order to save energy angular momentum conservation law, and this particle was observed in the experiments in 1956. And we have a complete unit on neutrino physics where we will discuss the importance of this particle. Therefore, we have linear momentum conservation law, energy conservation law, angular momentum conservation law, and then related to this, we have the threshold energy of the reaction, which is again an important concept and which is based on the energy conservation law. And this we will start discussing tomorrow when we will introduce the fact that how we can say that a reaction A plus B will give rise to 1 plus 2 in the final state, or it will give 3 plus 4 plus 5 particles in the final state. For example, an electron proton can give me an electron proton in the final state. It can give me electron proton plus pi 0 in the final state. It can give me electron proton plus pi plus pi minus final in the final state. But the energy requirement in each case will be different. How much energy an electron should carry to execute a process like we have electron plus proton plus 2 pions in the final state, or n number of pions in the final state, or similarly we have a photon striking a proton and we have a proton and a pi plus and a pi minus in the final state. That is known as the threshold energy of the reaction. We shall start the discussion on the threshold energy of the reaction. It is part of energy conservation also, and then we will move further to discuss the other conservation laws. Thank you very much.